My name is Lucian. I'm a staff engineer at Garmin. We're going to look at concurrency in this talk. We're going to look at the past, present, and future, but we are not going to insist that much on actually describing concurrency models in the past or the present or the future. We're just more trying to build a framework for us to be looking at those concurrency models and try to evaluate different models, and then try to find out if we can gather the lessons that we learn and put it into a new model. A lot of things that I'm going to say in this talk are experimental, so there's a huge risk involved in this talk. So first lesson, always declare the risks up front. And there are so many things that can go wrong, from broken laptop to the experiment. I do have some more interactive setups in here, so a lot of things may fail. But anyways, let's get started. So first, spoiler alert, concurrency is hard. Does anybody believes it's the other way around? Good, we're in the right scene. Some would even argue that it's harder than public speaking, although that's hard as well. Actually, there are studies that public speaking is here more than that. So to put these things together is like concurrency is very hard, right? It should be harder than that. Well, yeah. Most of the material I'm going to cover here is written in my latest article in Overload, in search of a better concurrency model. So this should appear in this month's Overload. And I just realized this is my 20th article in Overload, so I do have some experience with the Overload magazine. And I like to take this opportunity to thank Frances for all the great work, and the editorial team, like, really, really appreciate it. Thank you very much. Okay, so all the materials, the slides and photo copyrights and some more information, you can find it in this link. And while I'll keep this open, I need one volunteer to help me make concurrency less hard. Not much. Felix, thank you. So the requirement is that you can walk. I think you can do that. You can read. I think you can do that. So during the presentation, there will be a few moments in which I will ask you to come to stage and ask you to do different things. So just be prepared for that. Thank you very much. Okay, the agenda is pretty simple. Concurrency model, concurrency goal, past and present models, and we'll try to look at the possible future. Let's start with concurrency model. This is a little bit more theoretical, and there may be a gap between the theory and the examples that I'm giving below, but you really need to grasp this thing in order to fully understand what's in there. If you don't really grasp it, it doesn't quite matter, but trying to be as precise as possible for some areas. So concurrency, what is concurrency? First is a set of rules describing how the program is structured. These set of rules tell us how multiple activities can potentially be executed in overlapping time periods. It doesn't guarantee us, but it tells us what are the possibilities of doing that. And in another way of looking at it is you have a set of activities and you define a partial ordering for that set of activities, right? So that's concurrency. It has nothing to do with the actual execution of the code. In fact, you can reason about concurrency just by looking at the code. The code should not necessarily be running. On the other hand, parallelism is the simultaneous execution of activities, right? So it's the actual thing that runs. So let's take an example. We have two activities here, put it by our two rectangles, And by the diagram, I'm signifying the fact that they can be concurrent. They may run in parallel, or maybe not. If they are executed this way, then the program is both concurrent and parallel. However, if they are executed in this way, the program is just concurrent, but there is no parallelism involved in here. At runtime, we don't see two activities run at the same time. Right, so concurrency is about design time. It's independent of the hardware, and parallelism is about runtime. It's dependent on the hardware. We also will be talking from time to time about hardware threads or cores. Those are the things that enable parallelism. If I have a computer with 10 cores, I can theoretically run 10 activities in parallel, but I can't run 20 of them in parallel. Software thread is the thing that gets to our program, is the abstraction that allows us to express concurrency. And in this talk, we are going to focus on concurrency, right? Not on parallelism. I know parallelism is the goal for many applications, but concurrency just enables parallelism, so we're focusing on that. We're just mainly focusing on the rules of overlapping activities. And to give some examples, you may have rules that say two activities can run concurrently. Like if you spawn a thread, those two things will run concurrently. Cannot run concurrently. If you have a mutex, you're specifying that two things cannot run concurrently. You can have relations before and after, like this activity must run before the other activity, or the other way around, or you can have different other rules. And we're also going to cover how those things are made possible, implemented, and different types of things like that. We're not going into all these details, but this is kind of the framework to understand the point of view of the talk. So let's take an example. I'm just looking at the POSIX pthreads, and I'm going to just pick on the creation and joining of threads and the mutexes. Those are the functions that pthreads, that POSIX exposes for that. Of course, they have parameters and return time. We don't care about those. And just by analyzing those things, we can reason about what we can express in our program. So for example, with those, we can express the fact that we can run activities concurrently or join concurrent activities. We can also express the fact that some activities should not run concurrently. Right? So the first two relate to creating threads and joining threads, and the other one with locks. We cannot directly express the fact that one activity happens before the other activity. We can do that indirectly, however, just by putting some functions around that thing. We can reason about the guarantees of this model. In this case, I couldn't find any sensible guarantees, so none. And we can reason about the possible problems: deadlocks, malign race conditions, blocking threads more than needed, oversubscription, high latency, and so on and so forth. I'm sure you're familiar with most of these problems, and you had nightmares with some of these, like I did. So that's kind of the theoretical framework we are trying to analyze. This is our point of view. So let's try to look at concurrency goals. So concurrency is hard, and we want to make it simpler. And for that, we want to set up some goals that if we meet these goals, we can say we have the perfect concurrent concurrent model, whatever. So we're going to look at 3 different levels: safety, how fast the concurrent model can be. I'm choosing this word fast because it's a little bit ambiguous, so it's not efficiency, it's kind of in between. And the ease of use of the model. So I'm looking at the safety as a blocker. If we don't have safety, like the whole thing goes away, right? We have a huge problem on our hands. So that needs to be fixed. If we look at the fast aspect, that's important. The main reason we are doing concurrency for most applications is we want to be faster. So yeah, concurrent model needs to be fast. The ease of use, because of all the other problems, it was mainly a nice to have. I hope by the end of this talk that I'll convince you that ease of use is as important, and we should treat it as important as the other two. Okay, let's analyze safety, or the lack of it. First, race conditions. The concurrency model should not allow undefined behavior caused by race conditions. So this is our goal. Whenever you see something like a letter S, F, and E, that's one of our 3 levels, and then a number that says this is the identifier of the goal, and I just put a name there like race condition to be easily recognizable. Then I have the rule. This is a goal that we may want to have. And Felix, it's now the time. So, let me turn this on. So we have here a piece of shared state. Let me show to the audience, this is a shared state, obviously. You can take that thing, please take it slowly.
Yes.
You can read it and you can put it back.
Mm-hmm.
Now, slowly, try again reaching for that and take it. Take it. Take it.
I lost.
You lost, but
yeah.
That's typically what happens when we deal with shared state. 2 threads try to get the same shared state, and bad thing happened. In this case, the napkin was not actually broken, but it was severely damaged. So
yeah.
Okay. So that's the first thing. Please remain here. We have some more things to come. Deadlocks. The concurrency model should not allow deadlocks. So let's try another example here. We have 2 actors. Each one will try to take, there are 2 cards over here. Each one will try to take the left one first and then the right one, right?
Okay.
You do that first, I'll do that second. And that's the only rule. That's the only activity that you're allowed. You take the left one and then the right one.
Do I have to put the left one back?
No. When you're done with it, you can show it to the audience and then you can put them back.
Okay.
So let's try it. Left one. Right one. You do your work.
For those it's written concurrent.
You put them back, right? So that's the activity. Now, let's try it one more time. Now we have 2 actors. You pick the left one. You never know what the other actor is doing. It's picking the left one. And now we shall proceed. You pick the right one. I'll pick the right one. And
yeah, I cannot proceed.
I cannot proceed. So that's the problem. Like, that's the actual thing that happens in live code, and that's all over the place. This was kind of a silly example. You can get my point, right? We've all seen that. Starvation, it would have been nice to have that as a goal, but unfortunately, there's not something that a concurrent model can guarantee because this is dependent on the problem. So those are the two goals we have for safety. What about being fast? You know, things get more interesting in here. The first goal is scalability. For applications that express enough concurrent behavior, the concurrency model shall guarantee that the performance of the application scales with the number of hardware threads, right? So I have an application that has a lot of concurrency in it, and I put more hardware threads, I need to get an improved performance. We all know about Amdahl's law, not necessarily taking this too much into account. Like, I'm talking about it should scale. I'm not talking about perfect scaling, right? So if I need to process 1,000 elements and each element takes 1 second to process, then if I have 10 cores, it's about 100 seconds to process that. If I have 20 cores, it's about 50 seconds to process that, right? Amdahl's laws tell us it's going to be 50 and something, but that's not important, right? The important fact is that if I add more hardware threads, I'll get better performance. Okay, blocking. This one is one that frustrates me a lot because I keep talking to the comment was that I acquired the resource and not yet release it. I still need the resource, and that's a perfect example, thank you, for how I can waste system resources by just making them sit idle on the stage. Thank you very much. So, I was saying this frustrates me because I talk to a lot of experienced engineers, and they all argue like blocking is not a major problem. Like, yeah, whatever, it's not a big deal. It is. So let's say I have thread 1 that's doing some activity, and it requires a resource. Let's see, Felix is the resource here. And while we are doing this talk, Felix, at some portion of it, is required to be sitting on the stage. Now, different time, another thread comes and gets that resource. And the thread cannot proceed until that resource is free. So if the resource is busy, the thread simply have to wait. So that red part in the middle. But even worse, it's not just about 2 threads. There may be other threads who are just waiting on the second thread, and they all get blocked. Trust me, I've seen cases, I forgot the numbers, but it was something like a system that should be near real time, produce a response in a limited amount of time, was sitting minutes just because they are waiting on something else and something else. It was something like a chain of 13 locks waiting on each other. Like the first lock was waiting on the second lock, and the second lock was waiting on the third lock, and so on. So this is really bad. Okay. So now I'm going to ask Felix to do the following thing. For the rest of the talk, I'm going to need a book that I got from Matthew. And that book is now handed to Dom in the Empire State. Can you please simply just go, walk, don't run. We don't want any safety things. Just walk to Dom and ask him for the book. He knows somebody will come, so thank you. And now we're blocked. And you're blocked. threads don't get to unblock, right? That's not something we usually do. I think the resource is approaching. The system is a little bit crowded, so the resource is having time to come back.
So here you are.
Thank you very much. So now I can proceed. So I will be still requiring one thing from you. So, and Dom sent me a message. He said, I have no clue what is going on, either with this request or with life in general. And yes, right like a 5-year-old. And yeah, I was lucky yesterday. I found one of the books that I keep wanting to buy, Communicating Sequential Processes, in the hallway from Hubert. So that's really nice. I'll be using this later on. So if you'll be frustrating by this wait, like that's a good thing. I hope you're not going to pass this frustration on from now on. Please avoid blocking your threads, right? The threads or the other peers may feel the same frustration when you do that. So mutexes and locks in general can dramatically reduce the performance, right? Those tend to accumulate, the performance farm tend to just grow exponentially. And yes, a mutex is by definition a bottleneck, right? It prevents you from doing work. So think about mutex as bottlenecks. Okay, another problem which is very closely related to this one, oversubscription. The concurrency model shall allow limiting the oversubscription on hardware threads. And I'll have an example here on the slide, and then I'll have another live example as well. So let's say we have 2 threads, and we only have one hardware thread or core available to run them. We can either run them in sequence, run the first one and then run the next one, or we can run them in parallel. And this time I halfly mean parallel because at the hardware level it's not going to be parallel, but I'll try to pretend as if it's parallel. Let's pick the one in which we create two software threads and try to fake that we run them in parallel. Naively, we would expect both of those tasks to complete in 1 second. Let's assume those are CPU intensive, so the bottleneck is actually the CPU. You have only one CPU, you can't put that CPU to both activities, right? So that means you just have to switch around between those two. So that means the activities will take 2 seconds, if we're optimistic. But because you're switching constantly between software threads, there is an overhead in there. So it's always 2 seconds plus something. May not be much, may not be detectable, but it's always more than 2 seconds. Let's say 2.1 seconds, just for the sake of example. Is this good? Obviously, it's not good, because we thought we were getting 2 activities done in 1 second, and we got them done in 2.1 seconds, both of them. The alternative is to execute them one after the other. So that means the processor doesn't have to switch between activities. In that case, we can complete the first activity in the first second, and then we can complete the second activity by the second second. You get my point, right? So not only we completed both activities faster, but one activity it's after 1 second, not after 2.1 seconds, right? So from the point of one activity, it's much better, and the other activity is slightly better, right? So oversubscription is generally bad. We tend not to think about it, but this is a major source of slowness in the application. When you create too many threads and you have very few CPUs to run on. And now we'll bother Felix with another live demo. So this here is the actual first word of this book. So Felix, can you please read the words?
For a variety of reasons, this is a book eagerly awaited.
Okay, you were a little bit slow on that, like 5 seconds to read that thing. Can you keep the same pace when reading?
I think so. I hope so.
This is kind of the second one, please.
To say that their patience has been rewarded would be an understatement.
Okay, roughly about 5 seconds. You increased your speed a little bit, but roughly the same. Now, what I'm going to do is I'm going to ask you to read the same sentences, but one word from the first one, then the second word from the other one, and then another one from there, and another one. So like for, to, say. Ready?
Yeah.
Go.
For to say verity that of their reasons patience this has is been a reward book would eagerly be awaited, an understatement.
You've been much faster this time.
Sorry, I practiced. Yeah.
So the point is, like, if you would given the same speed, if you were reading at the same speed, this would be much harder for you to actually read, because you're constantly jumping between things, right? So normally, if you read this one, it would roughly take you 3 seconds. And if you read this like that, it will take you 10 seconds instead of 3 plus 3 seconds. Would you agree?
Yeah, I think so. Context switches are bad, not only for computers.
Good. So does that make sense for the audience? Like, I really want these things to be felt as really problems, because we can't put up good concurrency models if we keep ignoring these two problems. Does that make sense for the audience? I see no question. Thank you very much. Really helpful. I told you there are several things that can go wrong. Knocking the equipment out of the stage is one of them, so I just did that. So it's really important that we see these two problems together. They are tightly related. If oversubscription would not have been a problem, then we would not have such a big problem with the no blocking requirement, right? If you can just switch threads and it would be as fast as just running them sequentially, then you can create a lot of threads and just block them. It doesn't matter, provided that you have a lot of resources. But that's not the case. So oversubscription is the reason we can't use blocking primitives in our threads. That severely hurts performance. And again, don't get me wrong, I'm putting these as goals. It doesn't mean that there is no application in which you should not put a mutex in there. There are some valid cases in which you should put a mutex. But that's not a good general model. It's really bad on performance. Okay, synchronization. Let's move on to our fourth fast goal. The concurrency model shall not require any synchronization code during the execution of the task. except concurrency and control code. So whenever we are saying you have to start this or you have to end this activity. This is somehow similar to the F2, which is no blocking, but it's more general. What it tells you that you should not try to do atomics, you should not do compare and swap loops, you should not do any of those things. And the reason for that is it's adding cost, right? So each time you're doing, let's say, a cast loop, you're adding cost to your thread. If we want our code to be fast, you should try to remove that. May not always be possible, but that's why it's just a goal. Memory allocation. And we'll be discussing a lot of this because this is really important. The concurrency model shall not require dynamic memory allocation unless type erosion is explicitly requested by the user. Right? And again, the reason for that is memory allocation is expensive. Like if you really want your concurrent model to be fast, this is an expensive operation. You can't just do a memory allocation everywhere. So that kind of concludes our fast set of rules. We have a few more rules about ease of use. Okay, structured. The concurrency model shall match the description of structured concurrency. And this is something that I presented last year at ACCU. You can check up my talk. If you don't capture this QR code, you can always find it in the slide notes. Basically, I tried to take the goals of structured programming as defined in the 70s and try to apply them to concurrency. So we need to have abstractions as building blocks, recursive decomposition of programs in terms of those abstractions, local reasoning, single entry, single exit point, soundness and completeness, right? Remember the famous Bohm-Jakubini theorem that says every program can be written by selection, iteration, and the sequence, right? Of three control blocks. So in order for us to have an easy to reason about concurrent system, it needs to be structured. You need to have those 5 things in there. Negative examples, thread and locks. We don't have a good abstraction for that. You can't say this is a concurrent code. You can't just put that this is a thread or this is a lock. The abstractions are kind of more low level. You can't decompose your program with those abstractions and all that. Hope that kind of makes sense. If not, please see my previous year's talk. Another goal, which we don't often think about it, but it's very important. Concurrent code shall be expressed using the same syntax and semantics as non-concurrent code. Right? So if you're learning a language and you're learning to program concurrently in that language, if the concurrent part is completely different from the non-concurrent part, you're basically learning 2 languages. So it's far more complex. I have, painfully, I have a good example of that. As much as I love senders and receivers, this miserably fails this goal, just because you have to learn a completely new model for expressing your programs. And the model is very different from what people are used to in general imperative programming. Actually, true fact, I gave a presentation at CPPCon last year. And after the talk, a pretty visible member of the C++ community came to me and said, like, yeah, it's all great, but this will never be used. Just because it's too complex and it's too hard to understand. And there's some truth in that, right? This is a great model. Don't get me wrong. It's a great model. but it's not something that you want to point beginners at. Function coloring, which basically says function coloring should not be required for expressing concurrent code. The term function coloring comes from Bob Nystrom, had a nice blog article, What Color is Your Function?, in which he tries to explore how you can express different concurrent and not necessarily concurrent abstractions in the language, I think it was JavaScript. And he remarks that you make some certain conventions that tends to be pervasive at the function signatures. So one negative example, this is from C#. You have a regular function that returns an int. And if you want to write an async function, you have to put that async keyword, and you have to wrap the result in this task thing, right? And each time you want to do that, you basically have to write those things. So you have two types of functions. You have regular functions and you have called functions, async functions. This is not just present in C#. The C++ has it as well. It doesn't have the async keyword, but it's kind of the same thing. So you see the pattern, right? If we have two types of doing things, then we have two colors. And it's getting hard to mix those colors and mix those functions together. The main problem, and we'll get to some example later, is that this is pervasive. Once I start coloring a function in this way, I kind of ought to color everything around it in the same way. Another goal for ease of use, except for concurrency control code, the user shall not be required to add any extra code in concurrent code versus non-concurrent code. So this is basically the same thing as don't add any synchronization things in between inside your activities, but look from a different angle. The reason is you don't want to pollute your code with things that are irrelevant to the problem domain. If you have those concurrent activities nicely split up, you don't have to pollute everything in between with those. Right? So synchronization should only be present in concurrent control code, and there we should have, we should be careful about performance implications, right? So hopefully that makes sense. Don't add more code that you don't need to. This one is kind of debatable, but somehow we need to capture it. Because partially is the most fundamental thing that we care about. The concurrency model should have a minimum set of rules for the user to follow to stay within that model. So if you're programming with threads and locks, you know about threads, then you have to know about locks, you have to know about how deadlocks are. And this is kind of the typical case for textbooks in concurrency. Like, I've been trying to skim a lot of textbooks on concurrency, and great ones too. They all have the same pattern. Like, they start with showing you how to create threads, and then they will go, well, wait, there are problems if you just create threads. So let's explore those problems, like race conditions and all that. And then they will teach you how to create locks. And then they'll have a chapter saying, like, we have more problems with locks, like deadlocks and all that. And then you will have a chapter on avoiding these problems. And then you suddenly realize that all your application is slow. So you'll have a chapter with tips on efficiency, right? All these things add burden to the user mind. Ideally, we should want to keep just the first one, the first set of rules. Like, this is how you create parallel work. And by that, I mean the different types of parallel concurrent work. And by that, I mean different concurrent arrangements, like these two activities can run in parallel, or these two cannot run in parallel, or this needs to run before the after, and other things. And that should be the set of rules that the concurrency model should require from the user. Don't pollute users' mind with things that they should not care. So I hope that makes sense to you. What I've done so far is I try to go over the three categories that we've defined: safety, being fast, and ease of use, and try to set up goals for each of those. If we match all those goals, then we probably found the perfect concurrency model. So let's look at some past and present models. And I'm not going to go into too many details, but I'm somehow expecting that people will say, no, this is not like that in my favorite model. There may be some hits and misses here, but in general, that's the picture. So I try to take different models. There are some models that I skipped just because they are way too different and it was hard for me to capture them. But basically, it's the classic threads and locks, the tasks one, C# asynchronous model, C++ coroutines, senders and receivers, and Rust fearless concurrency model. By the way, Rust has other concurrent models. I'm just picking on this one. And I put a green check mark if largely the goal is met by that model. I would put a yellow triangle if it kind of does, but there are some things that the user may want to watch for. And I would put this circle stop signs like, no, this is way too far, it's probably not worth. And to some point, this is subjective, right? So different persons may have slightly different interpretations, but they would not be far off from this. So let's take them one by one. So locks and threads, or threads and locks. Anyway you spin that around, it's a bad model. I mean, really bad. The only thing that it's good at is function coloring, just because it has no notion of you couple concurrency to functions. So there is no function coloring at all. And F5 is no memory allocation. That's kind of there. But if you want to do more complex stuff, then you need shared state. And typically, when you put that mutex or whatever in shared state, you kind of need allocation. But it's pretty good on that path. Or not, depending on the implementation. Tasks. When I say here task, I'm actually mostly thinking of my 2021 ACCU presentation, which I described roughly 2 task models. But you can substitute that for other task models like Intel thread building blocks. And there are more, which I can't remember. I always have problems with memory. On the safety side, you kind of see a pattern here. So the one that says no race condition is kind of not applicable. You have to do some manual taking care of. But if you follow the rules of the model and you really try hard, and maybe this is not a problem. With S2, with deadlocks, this is not a problem because we are not using locks explicitly here. And those safety things are kind of the same for most of them, so I'm not going to bother with them. On the fast side of things, tasks are pretty good, except memory allocation. So a typical task system require you to do a memory allocation each time you create a task. And if you have an application that creates a lot of tasks, that can be a problem. Depending on the case, it may be a smaller problem or a larger one, but it's still a problem. In terms of ease of use, this doesn't look quite good. So the only one that's green here is the fact that it doesn't require extra code. So if you just put things nicely into tasks, maybe I should have put here a yellow triangle. But let's say that if you put things here in nice things, you don't typically have to put extra code in between. C# asynchronous model. So in here, we are doing less better in terms of fast. So we do have blocking primitives, and we do have our subscription. As I said, these always work hand in hand. We do have memory allocation each time we're trying to use those things. And we do have function coloring. I just showed an example of that. And for C#, if you're not caring that much about performance, it's not a necessarily bad system, right? You have some oversubscription, but you typically don't care because you're kind of used to a lot of allocations everywhere. You can't properly control the costs. So doing a lot of blocking may not be such a bad thing. So in the context of C#, this may be a quite good model. In terms of ease of use, it's not as easy as other models or other things that can be. C++ coroutines is somehow copying a lot of things from C#, but it improves on the fast side of things. It still has a problem with memory allocation. So basically, each time you are creating a coroutine, you're more or less expecting a memory allocation containing the stack of stack frame of the coroutine. The sender and receiver model really shines on the fast side of things. I put here a yellow triangle on the memory allocation, but you should look at it as this is very good. It's just like 1 tiny % of the cases when you need that. And the reason why I put it there is for tiny examples, you don't need memory allocation. But as soon as you're building larger application, you can't just make everything a template function that has everything public in there and all the logic as templates. So you need to abstract your way out of there. And you're doing that by using memory allocation. So you do need that. You do need to pay that memory allocation cost from time to time. Okay, and Rust. Rust is a great language, don't get me wrong. But in terms of meeting the goals we set up, it's pretty bad. So it kind of fails most of everything that we laid out here. What it really shines is on S1, so keeping things out of data races. To my surprise, it doesn't do good on blocking. You can do deadlocks in, sorry, not blocking, deadlocks. You can have deadlocks in Rust. In this particular model, right? So if you're not careful enough, you're going to go into deadlocks. And the tutorial that they have for fearless concurrency actually walks you through that. And it kind of follows the same pattern, like, here's how you set up concurrency. And you will have this problem, and you have to fight this. You have this other problem, and you have to fight this. So all the problems that we have in there is kind of laid out in this model. And it's not surprising, because if you look really hard at it, it's kind of inspired from threads and locks. Now, funny thing, again, Rust is a great language, but like, I'm always thinking about, when I hear fearless concurrency, I always think back at Aristotle. In his Ethics, he defines virtue to be the golden mean of some things. And he had this specific example. He doesn't use the word fearless. He says that there is no word invented for that, but he clearly describes it. And he says courage is the golden mean between cowardliness and fearless. If you're coward, that's bad. If you're fearless, it means you're reckless. You face danger without thinking. You're just bringing danger to yourself. So it's equally as bad in terms of courage. So lesson learned, don't use fearless again. It has bad connotations. Yep. The question was, with locks and threads and oversubscription, does it take care of that for you, or do you have to manually do that? And here the model says it doesn't do that for you. You have to manually do it. So just to make sure that I'm clear, and I didn't stress out this point. So what I'm trying to highlight here is not what are the things that you can possibly do with that model, but what are the guarantees that the model give to you, right? Theoretically, you can use all these models, and yeah, the easy of use not, but most of them in the fast part, like you can do fast code with all these models, right? But it's not within the direct consequence of the model. I'll try to summarize this, and excuse me if I do a bad job of it. The question was, what's the relation between tasks and data flows? And more comment on is this biased towards C++ tasks as defined? And I don't think C++ has any tasks in the standard. If we think about concurrent models, we should be thinking exactly about that. Have activities which theoretically should not contain any synchronization code, anything, and we should care about the relationship between those two. How do we create a diagram of those activities, if you like? Right? That diagram can be in time, can be in different other contexts, but that's the main idea, right? We should be focusing about the link between those activities. Another big thing that can fail, the other ones didn't quite fail. My laptop hasn't failed me yet, so that's good. I'm going to describe not one experiment, but an experiment within another experiment. So it's going to be really, really shaky, and I have no idea whether any of those two experiments will succeed. I'm going to start from the Valve programming language that's being created by Dimi Raccordon and Dave Abrahams. It was first announced at C++ Now last year, and it was announced as an experimental language. Like, we're trying to do things, and maybe they would work, maybe they wouldn't work. We just have to try and see it. And the three main goals that they set up for this language is fast by definition, safe by default, and simple. I think you kind of see the pattern here, right? It's kind of match my three levels of description. So that was the first experiment. Now an experiment within the experiment. By the way, for the first one, we don't know whether that experiment succeeded or not. We are still working on that. We're still missing a lot of things, like a good compiler. the experiment within the experiment is how can we design a concurrency in this model that would be coherent with the rest of the language and would adhere to the goals of the language. And specifically, we would want safe concurrency. We would want the concurrency model to be as fast as sender receiver. So I take that as a high bar for a fast concurrency. Or if you can't match it, be close by. You have to realize that each time we change something, it's going to affect the performance of things. So performance will never be equal. And in terms of ease of use, the initial goal was that we don't want function coloring. So we want easiness, but no function coloring. So we're going to look at C++ coroutines and senders receivers and try to take kind of the best parts of them and improve on those things, right? So we're going to try to take the performance from senders receivers and some ease of use from coroutines and then fix some of those things and also fix the safety problem. The main gray area that remains is the memory allocation thing for reasons that I'll explain in detail. So let's start with some simple example. This has no concurrency in it, so it's meant to be single-threaded. So we have a long task, a pretty dumb function that sleeps and increments a counter. We have another task that prints something that returns a number. Then we have an example that runs those two functions and then sums up the result. In Val, functions are doing what they promise they do. So if you see a function that takes an int and returns an int, that's everything that it does. It doesn't have side effects unless you go unsafe. So it's kind of like pure functions. Now, this is single-threaded. Let's add concurrency to this example. That's basically it. We say we want to spawn a thing, so we fork the execution path. Then at some point, we want to join that thing. So for that, the current idea is to introduce a new keyword, span. And spawn will basically make sure that there will be another activity running in parallel. And to join, we can simply use a function call or something like that. Spawn returns a handle, and that handle has a bunch of operations. Does it kind of make sense? I know you're not familiar with this, or most of you, but it doesn't seem that bad, right? Let's try to have the same example in C++ with coroutines. So long task is kind of the same, greeting task is kind of the same, but we can't put long task on the different threads directly. So what we are going to do, we are going to wrap it into a coroutine, and then this is just slideware. This doesn't compile necessarily. So we enter a thread in this coroutine, and then we run the long task on that thread, and we return that result. And then at the caller side, we can get the handle, and later on we can call with it. Doesn't matter the details here, but the point is you can get the same idea. Coming back to the previous point about task flows and data flows and tasks, this is the representation of the program. Right? People should know to reason about this and should not look at every comma and every function call that we have in the program. That's the main idea of ease of use. And in terms of concurrency, there are two important parts. There's the part in which we fork the execution. That's when the spawn keyword is used. And then there's the part when we join those things together. So that's when await is used. Please note another important thing. And this is very, very important if you start thinking about this model and how it operates. I'm entering on one thread, and because long task is long, that's the thread that is going to finish my execution. So my whole example starts on one thread and exits on a different thread. Although I have it in what syntactically seems like a single function, and in val it is a single function, the entry point is in one thread and the exit point is in a different thread. This is an important thing. And I've been thinking about this and try to conceptualize this whole thing and try to prove that this is a model that can be used for a lot of other applications. And the term I use for this is computation. So we can say this is a computation because it has one entry and one exit point, and you can switch threads in the middle. So you can think of it as a generalization of a function, right? So it may look like this, have a lot of concurrency in between, but from the outside world, it just looks like a function. We have one input and one output. You should simply forget about the fact that they may return on the same thread on a different thread. And this more theoretical notion of computation is something that we can see in practice. So senders from the senders receiver proposal are computations. C++ coroutines can act as computations. C# coroutines act as computation, and val coroutines also behave as computation. Basically, what I'm doing here is I'm trying to generalize a function into something that's appropriate for concurrency, but we already have that generalization of a function. We just name it coroutine for some time now. So you see there at the bottom, there's val coroutines. So basically what we're trying to do is try to define a coroutine model that matches this concurrency model, and that will lead us to our goals. Again, if you're more interested on the details, you can find them on my last year talk, and that explains what a computation is, how you can recursively build your concurrent programs based on computations, how to do local reasoning and all that. So let's go over the three layers that we defined. And we are going to start backwards this time, ease of use. So structure concurrency. We're going to use computation as the main abstraction. Again, that's the thing that we've discussed. Abstraction as building blocks, recursive decomposition, local reasoning, single entry, single exit point, soundness and completeness. These are all tied to the concept of a computation, right? And once more, this is the talk, you should go for more details. So, trying to say this multiple times with different words. So, in val, a function is always a computation, and those get implemented in terms of coroutines. And if we do that, then concurrency is embedded within functions. The user doesn't need to do anything else. They just need to write functions. And we probably all know how to write functions, so hopefully that's going to be an easy model. Local reasoning, that's guaranteed by val even more than the other languages. There are pitfalls in which even a single-threaded application can have safety safety problems because you're not able to do local reasoning. And basically, in order to guarantee the absence of these problems, you just have to be able to reason about the entire program, which is obviously not easy. In Val, if I have these three functions, I really don't care what I put inside long task. I know it's a function. I know it has one entry point. I know it has one exit point. They may be happening on different threads, but I don't care. And the language kind of makes me not care about this. Second goal, same syntax and semantics. We're just using functions. Like in C++ with coroutines, we're writing this code, and you see that we need different syntax, different semantics, or co-wait, co-return. We also need to color these things with tasks. But in Val, it's just, yeah, it's a function. Nothing more, right? So if you just ignore that spawn keyword over there, it just looks like a simple code. Function coloring, that's the problem we started with. We don't want function coloring. And I'll explain why this is, and I'll try to give an example. Coroutines are pervasive because the color of a coroutine tends to be another coroutine. So let's just take this C++ example. Let's say that in F1, we want to do some special concurrency, and we say, we have the tool for that, coroutine, so we'll package that up in a coroutine. But in F2, cannot finish on a different thread because it's a regular function. So I need to apply this to F2 as well. And then I need to apply this to F3, and I need to apply this to F4, and finally I need to do something into main because of this, right? Main cannot exist on a different thread, cannot be a coroutine, so I need to sync weight on this. Right? So you see how this is pervasive. So I start with one thing that I want to put concurrent logic in it. I need to color it, and then I need to color the entire stack down. So that's why this is a problem. If we have a concurrent intensive app, that means most of the functions will be coroutines if we follow this model. By contrast, in Val, there will be no function coloring. Like you just have regular function, regardless of how many threads you're using in there. Right? It's just regular, simple code. Extra code. We don't need any extra synchronization. We have safety by default. I'll come back to that in a bit. So why synchronize? This model doesn't require explicit synchronization. Yes, sometimes we want to pass messages. I discourage that thing, but that's outside of the model. That's something that we may want to optimize some of the things. Remember when we set up this goal, we said no synchronization except concurrency control code. Well, we just have two types of that thing, when we start an activity and when we end the activity. So that's when we have a spawn or when we have an await. And in Val, spawn of F would be equal in terms of sender receiver to something like this. I'm going to schedule something on the global scheduler, and I'm executing that F on the global scheduler. Or if F requires more threads, I'm going to do that global scheduler schedule, and then I'm going to let the value F, meaning that it passes around as a coroutine. If you're not familiar with sender receivers, don't worry. It doesn't matter that much. I'm just trying to put here equivalence things just to highlight the point that they tend to be equivalent. The performance, however, may slightly differ. I'm going to cover that in a bit. Await can be thought of in terms of sender receiver as a when all from the current work. So that's something like getting the current thread and I'm just putting it here, and then the work that I'm awaiting. And of course, we have generalization for this. We may want to have different schedulers, and we want to have spawning and joining on multiple activities. That's fine. The model can support that. That's not a problem. Another goal, and the final one for ease of use, is the minimal set of rules. Now I repeat the goal. The concurrency model should have a minimum set of rules for the user to follow to stay within that model. So in our case, that's a typo. If I told you things will go wrong, this is a typo. How work is being spawned, we have to have some rules about that. How work will be joined, we have to have some rules about that. That's it, nothing more. We don't have any rules for synchronization, we don't have any rules about sync-async distinction, and we don't have rules about how to prevent safety things, how to ensure that the performance is decent, how to write usable things. We don't have all that. We just have those two things, the start of concurrent and the end of concurrent work. Hope that makes sense. Let's get to the fun part, which is how fast this model can be. If we just take on from coroutines, we get scalability, blocking, our subscription, and synchronization, just take them from free. There's nothing special in there, just kind of course, C++ coroutines don't have the library implementation of task, which can, should provide all this, but I'm assuming that we can write that thing. The one that's tricky is about memory allocation. We don't like how C++ coroutines do memory allocation. They require dynamic memory for stack frames. Each time you call a coroutine, you have to find out the space for the stack, and you have to dynamically allocate that memory because you never know to which you're passing that. You do that for every call of a coroutine. And the problem is aggravated by the fact that you have pervasive coroutines, right? So you start with a coroutine and you have all the stack up until the bottom. You have to transform everything into the coroutine, right? So that doesn't work. I'm sure Dietmar will tell you on Saturday that we can make it work. But in general, as if we think about concurrent intensive application, this is not a model that scales well. It has efficiency problem. Now, what can we do? Well, if we look at the literature, there are two types of coroutines. There are stackless coroutines and there are stackful coroutines. The stackless coroutines store one frame at a time, so they need less memory, but they only can suspend in the call function. The stackful coroutines store the entire stack, so they need more memory, but they can suspend everywhere. So if I'm just stopping here, I can put it in there, I can just walk the stack. I don't have any problem with that. The stackless coroutines are used by what's now become the standard of C++. So C++ coroutines are stackless. And for stackful coroutines, there is this nice implementation in Boost. So coroutine 2 is one way you can go that route. We've discussed that C++ coroutines will not scale up in our context. So the idea is, let's try the other one and see how we can get it. So this is the trickiest slide in my slide deck. The cost of these things. For stackless, the main cost is associated with the calling of the coroutine, because each time I do a call, I need to allocate the frame for that. So it's a dynamic memory allocation cost for each call of the coroutine. And if all the functions are coroutines, then basically for each function call, I'll have a memory allocation. This is way too big of a cost. For stackful coroutines, I'll have costs whenever I'm spawning and when I'm exceeding stack space. And depending on the implementation, there may be different gotchas here and there, how you do things. But the point is that while you're doing memory allocation for calling each time, for stackful coroutines, you only need to pay the price when you spawn something, which should be more infrequent, far more infrequent than doing function calls. And I don't have any data to back this up. So